In this video, we are going to learn about the stack data structure. So we will learn about implementing the stack data structure, where is it used, and how is it used. So first of all, what is a stack? A stack is a last in, first out, or LIFO container. So what is a last in, first out container? So a LIFO container will have something like, if this is our stack, then we can put any amount of data in it. Let's say we put in 1, 2, 3, 4, 5. So we have 5 numbers, 5 integers in this stack. And the special thing about last in, first out containers or stack is that whatever operation we are going to perform on the stack will only be performed on one end, that is on this end. So if we are removing, or if we are accessing, or if we are adding anything, it will only be at the top of the stack here. So suppose I want to add another number, 6, it would be on top of 5. And if I want to remove a number, let's say we call the pop function. We'll learn about this function later on in this video. So it will remove 6. Let's say we want to remove the next element. It will remove 5. The next element to be removed would be 4. The next element to be removed would be 3. Now we can add another element, let's say 10. So that would be above 2. So whatever action we are going to perform will be on one end of the stack or one end of the array. So in other words, LIFO is last in, first out, and stacks can be implemented as arrays or linked lists. Also, where do we see stacks in real life? So, for example, if I have a table like this, then imagine this is my table. This is a table. So imagine this is your study table. And you put some books on top of it. So let's say this is book 1, this is book 2, this is book 3. So this right here is a stack of books. So just like we say in real life that we have a stack of books or a stack of objects lying around there. So just like that way, we have a stack in a computer program as well. So in real life, you would pick up the first book, and then you would pick up the next book, and then you would pick up this book. So even in a real life stack, we are only accessing the first element, that is the topmost element first. If you want to access the last element of the stack, you need to go through all the elements that are above it, and only then you can access the last element or the book that is at the bottom of your stack on your study table. So this is an example of a stack in real life. But where is a stack used in computer programs? So if you have ever used a computer calculator, you can see like 4 plus 5, and we hit enter. So the computer knows the answer is 9. But 4 plus 5 is not actually evaluated in this way. So this is something known as infix. So let's give it a bit of space. This is something known as infix. The computer, this is our infix expression, 4 plus 5. The computer does not evaluate in infix. The computer first converts this infix to postfix. So how will postfix look like? That would be 4, 5 plus. This is called postfix. So a computer evaluates according to postfix. In infix, you need brackets as well. So suppose you have something like 4 plus 5 times 2. In order to make sure that this addition is carried out first instead of this multiplication, you need to actually put 4 and 5 in braces. But in postfix, the braces are not needed. So if this is the infix, the postfix for this would be 4, 5 plus, and then 2 multiply. So in postfix, we never need braces. The order is implicit. The order is already there. We just need a stack to actually evaluate this. So how do you evaluate using stack? Can be shown very easily. Let's say this is our stack. You can also imagine a stack just like your school bag. So you put something on the bottom of your school bag and then things on top of that, and then there are things just piling on top of each other. So just like that, there's a stack in real life, just like that, there's a stack in computer program. So we first, in order to evaluate this postfix expression, we first put in all the operands. So here 4 and 5 are the operands, and any operator like plus, minus, division, multiplication, these are operators. So we first put in the operands 4 and 5. These two are pushed into the stack. Then we say plus. Then we encounter this plus. As soon as we encounter the plus, we take out this 5, we take out this 4, we add them together, and then we push it back into the stack. Then we see this 2, we put it into the stack. Then we encounter this multiplication sign. We take out the 2, we take out the 9, multiply them together, and then 18. Then we see that we don't have any other thing after this. So 18 is our final answer. So this is how we use a stack in a calculator. In your mobile phone calculator app, a stack is used behind the scenes. Stack is also used in undo operations. So whatever I'm drawing right here, let's say this, 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 this. If I undo it, we can see that it is being erased right in the order that I'm drawing it. So if this is being drawn the latest, this will be erased first as well. So you can see that this is a last in first out order as well. So a stack is also used in undo operations. So let's list a couple of cases where stack is used. Stack uses. So first one, we see that it is used in evaluating postfix expressions. It is also used in undo, redo. These are two places where stack is commonly used. So how do we implement stack? A stack can be implemented using arrays or linked lists. What is a stack? A stack is just a data structure in which modifications are made to the data only on one end of the data structure. So if you are implementing it as a linked list, you can only insert elements at the end or remove elements from the end. If you are implementing it as an array, you also have to make sure that insertions and deletions happen on only one end of the array. Since you're only going to access the top of the stack, the time complexity will be big O of 1. That is constant time complexity. Let us now implement the stack data structure using arrays in C++. So here I have a bunch of test cases that we're going to run. And first of all, we need to make sure what kind of functions we have to implement. So in stack, what do we need to do? First of all, let's say if we need to push an element on top of, let's say, this element, if we need to push an element, that would be called a push, or the function push. So the functions would be right at the very end. So one function would be push. If you want to remove this topmost element, that would be a pop. If you just want to access this element but not remove it, that will be called top. And if you want to check if the stack is empty or not, it will be called is empty. So we need to implement these 4 functions, and then our implementation of stack would be complete. So let's go over and implement these functions. So first of all, I'm going to define my array of size 5. So first of all, let's say the size of our array is 5, or let's say 10. Then we can declare our array as having size of size. We can also declare a point variable with -1 as initialized value. So what is point variable here? Point variable will point to the top of the array. So a point variable will point to the top of the array. So when point variable is 0, we will return 1. When point variable is 1, we will return 2. So in any case, it is basically an index of the array. And when point variable is -1, we can say that our array has no elements or our stack is empty. So when our stack is empty, we have removed 3, we have removed 2, and we have removed 1. Then our index is -1. That is, our point variable is -1, and we can say our stack is empty. This means we have made this means that we have made the case that point being equal to -1 will mean stack is empty. So this is our assumption, and we will build our program upon this. This also means that isEmpty function is very easy to define since we already know what we need to do here. So let's see. So isEmpty will return a Boolean value, true or false. It can also return an integer value, that is also true or false. So if you need a reminder, 0 is false and non-zero is true. So bool is empty. And then we'll just check if point is equal to -1. Now we have isEmpty function. The next function would be push function. So push function does not return anything. It in fact takes in an integer variable. Let's say the variable's name is val. Now, if point is less than our size -1, then we can just push the value into our array. Else we know that this is stack overflow. So let's see what we've done here. The isEmpty function is easy because when, let's put this point here so that it's easy to know. Point equals -1 means our stack is empty. So we have already established that we are going to use this fact, and hence we can just say if point is -1, this returns a Boolean value. If this is true, it will simply return true. And we know our stack is empty. If point is not -1, we know our stack is not empty. So this is our basic foundation, just like a base case in recursion, if you know that. Then in push function, we take in an integer value. We declare it as void because push does not return anything. And then if the value of point is less than size -1, since size is 10, the size of our array, our array can contain 10 elements, 0 through 9 as indices. Point is less than size minus 1. We first increment point and then store the value into the array. So this basically makes sure that if our point variable is -1, it first becomes 0. And at array of 0, we store value. And at that point, when array of and at that point, when point becomes size -1, that is, if point is 8, this will still run, and we will get at array of 9 the value that is being put in. When it becomes equal to 9, that is less than size -1, so 9 is not less than 9, it will just go to else and it will print stack overflow. So since you are trying to push beyond what is possible, you're trying to push more than 10 elements, it will say stack overflow. Let's code the pop function now. So pop function will also not return anything. It will just go and basically decrement our point variable. So if point is greater than, so if point is greater than 0, we can say that point minus minus, else we can say or we can say that this is stack underflow. So what is this pop function doing? So if point is greater than equal to 0, that is, if our array has some elements, if there are any elements in our array, we will just decrement the point variable. We will just decrement the point variable, which actually points to the element in our stack, the topmost element in our stack. And at some point, when point is equal to 0, point minus minus will make it -1. That is, we have removed all the elements from our stack. And at that point, if point is actually less than 0, we will go to the else part and print stack underflow. And finally, we have the top function. The top function returns an integer value, and it would just be like our pop function. So we can just copy and paste. But instead of actually making point minus minus, we can actually return the value at point. But top also has to make sure that stack underflow is not occurring. And since top is returning an integer value, we also have to make sure to return some kind of an error, basically. Let's say we are returning -1, but you can also throw some exception, maybe here, or some error code. Okay, so our code mostly looks right. But we still have not explored what stack overflow and stack underflow mean. So let's go back to the drawing board and see what stack overflow and stack underflow exactly are. So let's say this is our stack. And the size of this stack is 5. So I'm going to push 1. I'm going to push 2. I'm going to push 3. I'm going to push 4. And I'm going to push 5. So right now, my stack is full, right? It has 5 elements. Now, what happens if I just push 6? This cannot actually happen. This means stack overflow. So you might have also encountered stack overflow errors if you just use recursion without any base case. because recursion also uses stack space basically. And if a function calls itself again and again, it will eventually run out of stack space and cause a stack overflow error. And that is another usage of stacks. So on the other hand, if we, let's say, delete our elements, so I'm going to delete this. Okay. So now I'm going to pop. So pop means 5 will be deleted. Then calling again, pop will remove 4. Then pop will remove 3. If I pop again, it will remove 2. And if I pop again, it will remove 1. So at this point, my stack is empty, right? Apologize for the handwriting, but at this point, my stack is empty, and is empty will return true right now. But what happens if I call pop again? If I call pop again, it will result in stack underflow. So there are two things. If you exceed the size of the stack, it will result in stack overflow. If you try to pop on an empty stack, it will actually result in stack underflow. You can also cause a stack underflow if you try to access the top of the element if the stack is empty, because there are no elements to find the top of, right? So basically, this is stack overflow and stack underflow. And we are accounting for these two in our push and pop functions, and even our top function. Okay, so now let's see if our test cases run as expected. Okay, let me explain the test cases first. So first of all, we just initialize our stack here, right? Then we check if the stack is empty. Initially, stack should be empty, so it should return true. It might not actually print true, but a non-zero value will mean true. So it might return 1, 2, or any non-negative, non-zero number basically, and that will mean true. So we are expecting true right now. Then we push 1, so it should be 1. Then we push 2, then we see that 2 is added to the right, so it should be 1, 2. Then we push 3, then 3 is added to the right, and notice that operations are taking place only at the right end of the array. So only at the one end of the array, we are making any modifications, whether it's removal or it's addition or looking at the element of the array. It's only at one end, and right end is the one that is being used here. So push 3 will make it 1, 2, 3. Push 4 will make it 1, 2, 3, 4. Then we say top, and it should return the last element inserted, that is 4. So we expect 4. Push 5 will make it 1, 2, 3, 4, 5. Pop will remove this 5 because it was added just now. Pop again will remove this 4 because it was added before 5. Push 6 will make it 1, 2, 3, 6. Top now should actually return 6. 6 was just added right now. Pop will remove this 6 and make it 1, 2, 3. Is empty should return false because we have 3 elements. Pop again will make it 1, 2 and remove the 3. Pop again will remove this 2 and only 1 remains. Then if I call top, it should only return 1 because only 1 is in our array, only in our stack, right? Pop again will just remove this lonely 1 and our stack will be empty. Calling top now will result in stack underflow. And calling is empty should actually return true. Calling pop should also result in underflow because our stack is empty. So on an empty stack, top and pop should both result in an underflow, and is empty should result in true. Let's run the code and see if our values match the expected values. Okay, so let's see. First of all, we get is empty equal to 1. 1 means a non-zero value, that is true. So that is correct. Now top is 4. That is also fine. Then top is 6. That is also correct. Then isEmpty should be false. False is 0. That is also correct. Then top should be 1. That is correct. Then we would have a stack underflow. And yes, calling top results in a stack underflow with a -1 as our value that was returned. If you recall, top returns a -1 whenever whenever there is a stack underflow. Then we have isEmpty, and isEmpty will return true. So isEmpty returns true. That is a non-zero value. Then we have pop, and this should make it stack underflow, and it is a stack underflow. So our program works as expected. So let's go over it once again. So what's happening right now? Let's rearrange it a bit so that it's clear. Okay. So first of all, I defined the size of my array as 10. Then I basically just declared my array. Then I declared a point variable that will point to the top element. Right now it's initialized to -1. Initialization to -1 means that our array is empty, our stack is empty. Now, we first of all defined our isEmpty function. IsEmpty function is the easiest one to actually make or define because we have point equal to -1 as the case when our stack is empty. So when point is -1, we just return whether it's true or false. So this statement right here returns true if the stack is empty or if point is -1. Then we wrote our push function. So push function takes in an integer value. And if the point variable has any value that is less than size -1, that is less than 9, then we first increment our point variable so that, let's say our stack is basically empty at the beginning. So -1 will be first incremented to 0. Value will be assigned at array of 0. And at the other end, if point is 8, we increment it to 9, assign value to array of 9. Recall that we only have indices 0 through 9 in an array of 10. So this takes care of this case that indices should be in the range of 0 to 9. Otherwise, if this condition is not met, we have a stack overflow. Stack overflow is basically just going over above and beyond what we can actually store in our array, in our stack. Stack overflow will not be as much of a problem or as much of an issue if a linked list is used, because a linked list is a dynamic data structure. But we are not going to cover it in this lecture. We're only going to use array here. Then we declare our pop function, then we define our pop function. And if point is greater than or equal to 0, that is, there are some elements here. So let's write it here. If there are some elements in stack, then we just decrement the pointer variable. Notice that we are not actually deleting the elements. We are just decrementing the point variable. We are just decrementing the point variable and it's pointing to one element that's below the current element. And then when we push it again, it will actually just overwrite any value that is above it. So in other words, we don't really need to think much about it. We just decrement the point variable. That's it. And if point becomes -1, then popping does not make sense because our stack is empty and it results in a stack underflow. The top function returns an integer variable. Notice that in push and pop, we use a void return type, but in a top function, we use the integer return type. So if point is greater than or equal to 0, we return array of point. That is the value stored at that location in the array. Otherwise, we just print stack underflow and return some error code, or maybe you can throw some exception if you use a try-catch block. So this is a basic implementation of the array, and it's a very useful data structure. Now, one thing you might be wondering is whether you actually need to do all this again and again in data structures and algorithms problems. And the thing is, you don't need to do any of this again and again. So if you wish to basically use a stack data structure, you can do so quite easily. So I'll just give a brief introduction with STL stacks. So we need to include stack. Then we can just say stack our desired data type and st or some variable name. This stack is built into data structures of C++, that is STL data structure, or we can say standard template library. Stack data structure. And we can pretty much perform all the same functions, st.push, st.pop, st.top, and st.isEmpty. So these functions, these are all defined. These are all in red right now because they're not in a function. Let's put them in a function. So we have pretty much all of these functions. IsEmpty is actually empty in our STL stack. And STL is built in, and you don't need to do anything. You don't need to define what we've done right here. You don't need to define any of these functions. The great thing about using STL stack or STL data structures in any sense is that you can actually use any data type you want. You can use a double if you want, or you can actually say, if you want to use float, or for some reason, if you want to use any of your class objects. So it can be any data type. It can be written as T. So T here stands for any data type you want to put in a stack. So how stack is internally implemented in C++ STL, you don't need to know that. You just need to use the stack as you wish to code your DSA problems. That's it for this lecture. Thanks for watching. Hope you learned something, and I'll see you in the next video.